This lesson is about collision detection, and it'll be fairly complex. Often in games and other programs, we'll want something to happen when two objects hit each other, such as having them bounce off of each other. And for this, we need collision detection, which is just figuring out which pairs of objects are colliding with each other. A lot of the time, we'll want to do this in real time, so our solution had better be pretty fast. It turns out that collision detection is hard, which is why the beta versions of games a lot of the time will have bad collision detection. And there's actually no one right answer for collision detection. It really depends on the type of program that you're making. Depends on a bunch of factors, such as when collisions usually occur in the particular setting of the program, and it also depends on which collisions are the most important, which flaws are the most noticeable, because you'll want to focus your effort on those types of collisions, whereas the other collisions that are less important don't have to be as accurate. Also, collision detection is a much different problem if you only care about collisions with a particular protagonist, as opposed to if you care about collisions between every pair of objects. And collision detection is a really big topic. I can only cover a fraction of techniques that are useful for collision detection. A lot of the time what you want to do is basically group together physically closer objects in memory somehow. And some collision detection algorithms utilize the fact that the scene doesn't change much from frame to frame. Also, you can get perfect collision detection by determining exactly which polygons intersect any other polygons of the other 3D models in the scene, but a lot of the times it's better to use approximations to approximate 3D models as cylinders, spheres, or boxes, because it's easier to check whether those are colliding with each other. Another useful technique is to have a quick and dirty check to determine whether two objects might be colliding. So for example, if you have a drawn out a check for two objects that might take a long time, then you could just first check whether their bounding spheres are intersecting before you waste time on a complicated check. And those are a few techniques that we can use for collision detection. I'm going to show you one particular method of collision detection which will be useful for our particular program that we're doing in this lesson. So here's the program. It's a box spinning, and it has 4 invisible walls actually that are out, in, and on the sides. And every time you press spacebar, it creates 20 balls. So you basically have these balls that are bouncing around in this box, bouncing off of the walls and off of each other. And this is the type of problem that we want to solve for collision detection. Now, let me just give you an idea of how this program works. What we'll do basically is give each ball a particular state, in particular the direction in which the ball is flying, and then we'll advance the positions of the balls by 10 milliseconds, and we'll check for and handle collisions. Then we'll advance their positions by 10 milliseconds again, and check and handle collisions again, and so on. We'll just repeat that. And since this is a lesson on collision detection, we're going to be focusing on the part where we figure out which pairs of balls are colliding with each other. One approach that we could use for this is to check every pair of balls. And for each pair of balls, check whether the distance between them is less than the sum of the radii of the balls. And this approach works, but the problem is it's really slow. In particular, if you had 500 balls in the scene, then you'd have to check over 100,000 pairs of balls for potential collisions. So let's see if we can narrow our search down a little bit. I'm going to show you one way that we could narrow it down. This will actually be an example of the 2D version of the problem, where we have a square and we have circles bouncing around in that square. So what we could do is just divide this square up into 4 smaller squares right here. Divide it halfway along each dimension, and then we can go through all the balls and figure out which square or squares in which they belong. And then for each of the squares, we can just take every pair of balls within that square and use those for our potential collisions. Check each of those for collisions. And that'll narrow down our search quite a bit. In this particular example, instead of checking 105 pairs of balls, we would only have to check 31 using this technique right here. So basically what we did is we took a large version of the problem, this outer box, and divided it up into 4 smaller versions of the problem, represented by these smaller boxes inside. And for each of those, we just took every pair of balls to be our potential collisions. But actually, we could divide the problem up even further. So we could take this box right here and divide it into 4 smaller squares right here. And just do the same thing for each of those squares. Take every pair of balls. And that'll narrow down our search even more. And we can keep on dividing these squares as much as we want, actually, although after a while it's not so helpful anymore. In particular, when we have few balls in a square, then it's easier just to check every pair of balls because there aren't so many pairs than to keep on dividing it. Also, once the size of the squares approaches the radius of the circles, then it's not too helpful to keep on dividing them, because then these circles will start to appear in many of the boxes. So you'll actually start increasing the number of pairs of balls that you'd have to check, because these appear in so many boxes. So what we're going to do basically is we'll use a recursive solution for a given box. We will check whether there are few enough balls in the box, in which case we'll just take every pair of balls. That'll be our potential collisions. Or if the box is too small, we'll also take every pair of collisions. Every pair of balls. But otherwise, we'll divide the box up into 4 smaller boxes, and then we'll ask each of its 4 smaller boxes for potential collisions. And we'll put those answers together. That'll give us all of the potential collisions in a particular box. And let me show you what the solution looks like over here. So this is the same exact problem. The balls are in the same positions. We divided it up into these 4 smaller squares, and the lower left and the lower right squares we're actually dividing even further into 4 smaller squares, since they have so many balls in them. And that actually results in a tree-like structure over here. So this node right here, this top node, represents the entire square. And this node right here represents this smaller subdivision, and then each of these 4 nodes right here represent one of these 4 even smaller subdivisions. So this is our tree structure. For a particular node in the tree, we can figure out the potential collisions by either asking all of its 4 children for their potential collisions, in this case, or if we're one of these leaf nodes, one of the nodes that doesn't have any children, then we just take every pair of balls within the node. And that's how we can figure out pairs of balls that are potentially colliding with each other. And this approach actually further reduces the number of pairs of balls that we have to check. Before we had to check 31, that was when we only divided it once, but when we divided it even more, now we only have to check 15 pairs of balls. So we've reduced our search space, which is nice. It speeds things up. So this data structure right here, this tree, it's called a quad tree. But actually we'll be using the 3D version of it, which is called an octree, which has 1 T for some reason, octree. So that's what we're going to be using for this project to make things go quickly. And let's take a look at some code now. Actually, before we get into the code for collision detection, I'm just going to explain the basic mechanics, the code that basically governs how and where the balls move, and things like that. So let's take a look. First, we have a function right here, random float, which will return a random float from 0 to 1 using this code right here. It's some standard C++ random number generation code. And we'll need that function in order to give the balls random positions and random colors, random radii, whenever we create them, whenever the user presses the spacebar key. So that's what the random float function is for. Now, let me explain a little bit about how we're going to have these balls moving around. So basically, each ball has a velocity, which is a vector. And the velocity indicates how fast the ball is moving in the x, y, and z directions. So for example, a velocity of 3, -2, -5 means that a ball is moving 3 units per second towards the right, 2 units per second downward, and 5 units per second in the negative z direction. So that's how velocities are represented. And the way that gravity works, and it's the same in this program as for real life, is it basically makes a given object, the velocity of a given object, decrease at a particular rate. So in the real world, for example, it'll make the y component of a velocity decrease at 9.8 meters per second per second. In our program, we have this constant right here, gravity, which stores the rate at which the y component of the velocity will decrease, which in this case will be 8 units per second per second. So that's this gravity constant. Then we have a box size constant, which is just the length of any side of the cube in which the balls are bouncing. Then we have this time between updates constant, which I mentioned earlier that our approach was going to be to advance the balls for 10 milliseconds, then to check for collisions, then advance for 10 milliseconds and check for collisions. This variable is basically the amount of seconds by which we advance. So it doesn't have to be 10 milliseconds, it's just whatever this variable right here is. And if you download the source code, this number will actually be 0.01, but I changed it to 0.001 to slow the program down, actually, to better give us an idea of how much we're speeding things up using octrees, because later I'll show you the difference between using octrees and a more straightforward approach. So if you're running on a fast computer, you'll probably want to decrease this variable if you want to see just how much speed we're getting out of this technique. After that, we have this variable timer ms, which is just the number of milliseconds between calls to the update function. So it's how often our timer function is called. So those are these constants. Then we have a ball structure, which stores all of the information about a particular ball. So it stores the velocity right here, the position, the radius, and the color of a given ball. The color is represented by its red, green, and blue components, just as a vector, because I'm weird like that. After that, we have this enumeration, which stores all the different types of walls. So we have the wall that's on the left, the wall that's on the right, and so on. That's this enumeration right here. Then we have this ball pair structure, which stores just a pair of pointers to balls. So we're going to use this to indicate potential collisions. Then we have a ball-wall pair right here, which is, it stores a ball and a wall, and we'll use this to store potential collisions between a ball and a wall. By the way, you might have noticed that I'm sort of skipping over collisions between balls and walls in this octree data structure that I was explaining. And the main reason for that is there aren't as many collisions between balls and walls. They're not as important, and it's not as big of a deal to speed them up. The real savings are when we speed up the collisions between pairs of balls. But we'll cover that later anyway. And here's our octree data structure. It's our octree class. I'm actually going to skip over it for now, because like I said, I'm just explaining the mechanics for now. So now we have this function called potential ball-ball collisions, which will figure out all the possible collisions between pairs of balls using by calling this method on the octree. And it'll store the result in this vector right here, potential collisions. It's actually a C++ vector, which C++ vectors are kind of like variable-sized arrays. You can include them by using number include vector, and you'll get vector objects. Over here we have the type of the vector, which is a vector of ball pairs. And vectors, you can access individual elements of them, just like in arrays, using brackets. You can figure out the size of a vector using .size, and you can add an element to a vector using .push_back. So let me just scroll up and show you an example of that. Here we go. We have .pushback, that's adding an element to the end of a vector. So that's what C++ vectors are. And this potential ball-ball collisions method just puts a bunch of potential collisions into this vector right here. So that's that function. Then we have potential ball-wall collisions, which finds out all possible collisions between a ball and a wall and puts them into this vector right here. And again, it does this just by calling one of the methods of the octree. And you'll notice, by the way, that below each of these I have a slow method of finding potential ball-ball collisions and ball-wall collisions. And the slow method is just basically trying every pair of balls and every ball-wall pair, which is the slow approach that I mentioned earlier, the way that doesn't work as quickly. And we'll be able to compare these two approaches later on. So we'll see just how slow the slow method is. And then we have this function right here, move balls, which is just going to take all of the balls and move them based on their velocity. So it'll add the velocity times dt to the position. dt is the amount of time over which we're moving the balls. And we also call ball moved with the octree on each of the balls, which we'll see that later. After that, we have a function called apply gravity, which is going to apply the effects of gravity to a particular ball over a particular time interval. So what it'll do is it'll decrease the y component of the velocity of each ball by gravity times the amount of time by which we're updating, which is time between updates. So this takes care of making it look like we have gravity applied to each of these balls. It basically simulates real-world gravity. And then we have right here test ball-ball collision, which is going to test whether two balls are colliding with each other. And it does that just by checking whether the distance between the two balls is less than the sum of the radii. Or actually it checks whether the distance squared is less than the sum of the radii squared, right here. Actually, if they are close enough, we want to do one extra check to make sure that they're colliding. So, if the balls are moving away from each other, then we say that they're not colliding, because that probably means that they just bounce off of each other. Though they're technically intersecting each other, but they're already moving away from each other, so we don't want them to bounce off of each other if they're already moving away. So we have to put in this extra check right here to check whether the balls are moving towards each other. And that's test ball-ball collision. Here we have handle ball-ball collisions, which is going to just find out all the potential ball-ball collisions and go through them and check whether they're actual ball-ball collisions by calling test ball-ball collision. And then, if there is a collision, which will happen whenever it reaches this part right here, what we want to do is change the velocity of both of the balls so it looks like they bounce off of each other. And basically what we'll do is we'll have them bounce off. We'll basically just reflect the velocity in the direction from one ball to the other. So let me show a little diagram of that over here. So here's the surface of the two balls, basically, which is perpendicular to the direction between the two balls. And here's the direction of the initial velocity of a ball. Here is the direction from one of the balls to the other ball. This is actually the projection of this vector onto that direction. It's called S. So in order to figure out this bounce velocity that we want right here, we're just going to take the initial direction and subtract twice this direction right here. So it's d minus 2s, this bounce velocity right here. And that's what we're doing over here. We're taking this vector right here, this is the s vector for the first ball, and we're just subtracting twice that from the velocity. And that's how we make it look like they're bouncing off of each other. And actually, all of the velocity is preserved when they bounce off of each other. They're not slowing down or anything. So that way, this program will actually run forever. They'll keep bouncing around forever. So that way, this program can give us days or even years of continuous entertainment. Or, not really, but whatever. Something like that. So, anyway, that's this function. Then we have a function called wall direction, which basically indicates the direction from the center of the cube to a particular wall over here using a switch statement. Then we have test ball wall collision, which tests whether a ball and a wall are actually colliding. And basically just what it has to do is check whether the ball is farther from the center than whether the ball plus its radius in the direction of the wall is farther from the center than the wall is. Or confusing to explain, but it's pretty straightforward. That's this check right here. And again, we have to check to make sure that the ball isn't already moving away from the wall, which means that it just bounced off of the wall. So we need this extra check right here. After that function, we have handle ball wall collisions, which is kind of the same idea as handle ball ball collisions. It goes through all of the potential collisions according to this function right here, and it calls test ball wall collision to see if it's an actual collision, and if it is, it just has the ball reflect off of the wall, again without losing any of its speed. After that, we have perform update, which is going to be called every time between updates seconds, which by default is 10 milliseconds. I've changed it to 1 millisecond. So what we're doing is we're applying gravity, and we handle all of the collisions. So it just calls all of these other methods that we've seen before. Then we have a function called advance, which just advances the state of the simulation by a particular amount of time. This t variable right here. And basically what it does is it takes care of calling move balls and perform update as appropriate. So what we want to have is we want to call move balls every 10 milliseconds, or actually 1 millisecond in this case, and then call perform update after that particular amount of time has expired. And if you read through this code, that's exactly what it does. It just alternates between move balls and perform update. And after that, we have all of our variables. We have the balls, the angle. We have an octree object, which is going to help collision detection. We have time until update, which is used in the advanced function that we just saw. And we have the texture ID of the floor and the ceiling. By the way, you may have noticed that in all of my programs, all of these variables right here begin with underscores. And the reason I'm doing this is because, well, basically, it's not usually a good idea to use global variables, which is what all of these are. They're global variables. The main problem with that is that in order to understand a program, or to understand a source file, you potentially have to understand all of these global variables and how they're edited, how they're used. It's a lot to keep in your head at one time. And it's actually easy to abuse the global variables, easy to make mistakes with them. So global variables are usually a bad idea. But in order not to distract from the collision detection part of this program, I'm going to use global variables instead of using a better approach, instead of using header files or something. And that'll just make it so we can focus on collision detection. But I still want to... What I'm going to do is I'm basically going to pretend that all of these variables, even though they're global variables, I'll pretend that they can only be accessed from a few select functions. From cleanup, handle key press, init rendering, draw scene, and the main function. And I think that covers it. Yeah, and handle resize. I don't know if I mentioned that. So, and update also. So I'm basically going to pretend that these aren't global variables, that they can only be accessed from those special functions. And I'm putting an underscore at the front just to make it obvious that I don't want to access them too much. That I only want to edit these variables in those particular functions. So that's why I'm using underscores at the beginning of all their names. By the way, C++ doesn't let you begin an identifier, one of these names right here, with an underscore and a capital letter, or with 2 underscores, but all these begin with underscores and lowercase letters, so we're good. Then we have this cleanup function, which deletes all of our ball objects and deletes the octree. Pretty straightforward. We have the handle key press function, which over here, when the user presses the spacebar key, it's going to add 20 balls to our scene. So 20 times it'll go through and it'll make a new ball object, and then it'll set the position to a random position, the velocity to a random velocity, give it a random radius and a random color, and then add it to our balls vector, which stores all of the balls. So that's that. Then in our init rendering function, just loading the texture in. In our draw scene function, we have right here we're drawing the top and the bottom of the box, which is all stuff we've seen before. It's just 2 quadrilaterals. Then we want to draw the balls in the scene, and that's right here. We're actually going to use a new function called glut solid sphere, which draws a sphere for us, basically. It just takes care of the details of finding out the exact vertices and things like that to figure out how we can approximate a sphere. And glut solid sphere takes 3 arguments: the radius of the sphere, and 2 arguments indicating how many polygons we want to use to represent the sphere. So the smaller the number, the worse it'll look, but the quicker it'll draw. So that's this glut solid sphere call. After that we have our update function, which just calls advance, which we saw earlier, and it increases the camera angle. And our main function, we have right here where we seed the random number generator. You just have to use something like this if you ever want to use random numbers, which we're using. We're using that random float function to randomly position the balls and such. And over here in the model, we're in the middle, we're constructing a new octree for the program. And that basically covers the mechanics of how everything works. I haven't actually shown you code for collision detection yet, so let's go back to that. Let's go to our octree class, which is up here. So first we have a few constants for our octree. We have the maximum depth of the octree, which is basically just, let me go back to this picture over here. It's just the maximum number of levels in this tree, basically. And we have that so that the individual boxes don't get to be too small. Like I mentioned, if we have boxes that are too small, then each of the balls will appear in too many boxes, which will slow things down. Then we also want to have a maximum number of balls in each of the octree nodes. If there are more balls, then we want to split it up further. And actually I'm going to have this thing right here, min balls per octree, which is going to make it so that if we remove a ball from an octree and then we bring it below this number of balls right here, then we're actually going to undivide that particular octree. We're going to just make it into one cube instead of 8. And the reason we'll do that is so that it'll be more appropriate when we have fewer balls. And I'm using 2 variables right here, using 2 different limits for minimum and maximum number of balls. So that way, if one particular octree keeps switching between, so if these 2 values were the same, then if one particular octree you were to keep adding and removing and adding and removing and adding and removing one particular ball from that octree, then you'd have to keep making and deleting and making and deleting and making and deleting children, which would just slow things down in and of itself. So that's why these 2 values are not equal. Then we have our octree class right here. That's our collision detection structure. We have 3 vectors right here, which represent the corners of the octree, the corners of the cube in the octree. So this is the lower left outer corner, and this is the upper right outer corner. Lower left inner, upper right outer. And then this center right here, this vector is just basically the average of the two corners. It's the middle of the cube. So these three indicate where exactly the cube is for this particular node in an octree. Then we have this array right here, which stores the children of the octree, if there are any. Sometimes there aren't any, but sometimes there are children, so we use this variable right here. And like it says in the comments, children 0, and then the next two can be anything. They indicate children whose x-coordinates range from min x to center x, from the x-coordinate of this corner to the x-coordinate of the center. And children 1 star star, the stars are just wildcards, they indicate the children whose x values range from the x value of the center to the x value of this corner right here. And it's the same idea for the other two dimensions of the children. So we're just using a three-dimensional array, basically, to store all of the 8 children of a particular octree. Then we have a variable that indicates whether a particular node has any children. We have a variable that stores all of the balls in a particular node if it has no children, which, switching back to this picture right here, you'll notice that would be these kinds of nodes right here that don't have any children. They actually have to store the balls, whereas the rest of them just have pointers to their children. So then we have the depth of the octree, which is the level of it in the tree. We have this numBalls variable, which is the number of balls in the octree node, including all of the balls in its children. We need to keep track of that number to know when we want to divide up or undivide up a particular octree node. Then we have a fileBall function, which will take care of either adding or removing a ball to the appropriate position of an octree. Actually, it'll basically just figure out which children that ball belongs in, and it'll either add or remove them from those children, depending on whether add ball is true or false. And to make life easier, we're actually just going to compare the bounding box of the ball with the positions of the cubes for each of the children, instead of comparing the actual sphere with the cubes for the children. That'll just make our life easier. So you can look at these loops right here, and they basically do what we want them to do. They figure out the appropriate children, and then they'll either call add or remove with the ball, which we'll see these add and remove methods later. Then we have this function called haveChildren, which just divides up a particular cube into smaller cubes, into 8 smaller cubes. So it takes all the balls that are currently in this node, and it makes children and puts those balls into those children as appropriate. And so using this loop right here, which you can look at, it'll just create new octrees, new octree nodes for all of the children right here. So it'll set up this children variable to store 8 octree nodes, and then it'll go through all of the balls in the node and call fileBall to put them in the appropriate children. And then it'll just clear the balls set in order to get rid of all the balls that are in the particular node. And it sets the hasChildren variable to true, because now this node has children. Actually, let me explain a little bit about the balls variable, which is a C++ set. Let me scroll up to it right here, set. You can use sets by calling by using number include set. And what sets are is they're basically a group of objects, a group of distinct objects. So every time we want to add an element to a set, we just call balls.add, and every time we want to remove it, we call balls.erase. So let me find some examples. We have, oh sorry, it's balls.insert if you want to add an element. And if you want to remove an element, it's balls.erase. So another thing you can do with sets is call this clear method right here, which just removes all the elements from the set. And if you ever want to go through all of the elements in a set, you just use this form right here. It may look kind of weird, but the basic idea is you have for set of whatever type the set is, colon colon iterator, and then a variable name equals the name of the set dot begin, and then the while condition is while the iterator is not equal to the set dot end, and then we have the iterator plus plus. Then we have we just use star it, star the iterator variable name, in order to get at the element that we are in this loop. So basically, you just want to use this format if you ever want to go through all of the elements in a set. We're going through all of the balls in this set using this construct. And that's the haveChildren method. Now over here we have a method called collectBalls, which just figures out which balls are in a particular octree node or in one of its children. So it'll figure all those out and put them into this bees array, which is a set. Bees set. It'll put it all into this set of ball pointers. So if this node has children, it'll just go through all of the children and call collect balls on those children. If it doesn't have any children, then it'll just iterate through all of the balls and insert them into the set. And that's all we have to do for collect balls. Then we have a method called destroy children, which just takes all of the balls in the children of the octree and puts them into this particular octree node, and then it deletes all of the children. So it just, in order to do this, we just figure out which balls are in this octree and in any of its children, and then we delete all of the children, and we set the hasChildren variable to false. Then we have a remove function right here, which is going to remove a ball from the octree, a ball that's at this particular position. The way we do that is we decrement the numBalls variable, and if the numBalls variable has just gotten smaller than min balls per octree, then we want to destroy all the children and move all the balls up into this node. Then, if there are children, we want to file the ball, or we want to call fileBall in order to remove the balls, in order to remove the ball from the appropriate children. But if this doesn't have any children, then we just call erase on the ball set. So we remove it from this particular node. And that's the remove function. This potential ball-wall collisions, I'm going to get back to it. So we'll just skip it for now. Then we have the constructor for an octree, which takes the two corners and the depth of the node, and it just initializes all the variables as appropriate. Then we have the destructor, which calls destroy children to delete all the children, if there are any children. And that's all we have to do for the destructor. Then we have the add method, which adds a ball to an octree node. And the way it does this is it increments the numBalls variable, and then if there aren't any in certain cases we'll want to add children to the ball, to the octree node, and those cases are when we don't already have children, and the depth isn't too high, and the number of balls has exceeded max balls per octree. That's when we want to add children. So that's what this if statement right here does. Now, if we have children, we want to file the ball away in the appropriate children. But if we don't have children, then we just want to add the ball into the balls set, which is this right here. And then we have a remove method right here, which is, it just calls the other remove method that we saw with the ball's current position. Then we have a method called ballMoved, which we're going to call whenever a ball changes position. And to do this, we're just going to remove the ball from its old position and then add it to its new position. We could do something more complicated, figure out exactly which octrees it now is in, but it wasn't in before, and which ones it was in before, but it now is in. But, too complicated. We'll just stick with this. It probably won't be too slow anyway. Then we have potential ball-ball collisions, which will actually find out all of the potential collisions between pairs of balls. And if there are children, we just go through all the children and call potential ball-ball collisions, which will add them all to this vector right here, collisions. If we don't have any children, then right here we're just going to go through every pair of balls, and we're going to add them to the collisions, or the collisions vector right here. So that's what this code right here does. And that's the potential ball-ball collisions function, or method. For the potential ball-wall collisions method, we're actually going to call a method that I skipped over before, which is kind of a helper method. And let's go back to that. So, to find out potential ball-wall collisions, what we're going to do is we're basically just going to, let me go over to here. If we wanted to find the potential collisions with balls and the bottom wall over here, we would just basically find all of the boxes that are down at the bottom, and then take all of the balls with that and pair them with this wall right here. So that's basically what this function is going to help us do. It's kind of long, but the approach is pretty simple. And this function will be called separately for each of the walls. It'll have a vector where it stores the collisions, the potential collisions. It'll have the type of the wall, and it'll also have the coordinate for the wall and the direction of the coordinate. So for instance, if the coordinate were the character x and the direction were -1, that would indicate the negative x direction, which means we're working with the left wall. And you can take a look right here. It basically does what I just described in this picture right here. And it does it separately for all the different walls. So using 6 calls to that helper function right there, we can figure out all the potential collisions between balls and walls. And that takes care of all of this octree business. Basically, we're just calling methods on the octree, which I showed you earlier on. And that actually hopefully speeds things up quite a bit. And I actually tested this out on one of my computers, and using this faster method, using octrees, it was able to have 1,000 balls and run about as smoothly as using the slower method with 300 balls. The slower method where we just check every pair of balls. And let me show you how you can compare these two speeds. You just go over here and comment out the fast method, and then uncomment out the slow method. This is for potential ball-ball collisions. You have to do the same thing for potential ball-wall collisions. Just comment out this fast method and uncomment the slow method. And a couple more things. Over here in move balls, you need to comment out the ball moved function, which is another octree function. And let me scroll down to handle key press, where we're going to add balls. There was a call in handle key press to the add method of octrees, so we're going to comment that out also. So if you save this and run it, you can actually take a look at how fast the program runs using the slower form of collision detection. So you can see how much we sped things up. And right here, I'll try adding 20 I'll try pressing spacebar 20 times. So you'll notice that after I press spacebar 20 times, which adds 400 balls to the scene, things are slowed down a lot, actually. It's moving pretty choppy. And let's go back and see what it's like when we're using octrees. So I'll just undo these changes. And I'll run the program again. And I'll just add 400 balls to the program and see how choppy it is with the octree. So it's still kind of choppy, but it's not nearly as choppy as it was when it was using the slower method. And that's because this octree has sped up collision detection a bit, which is nice. And actually, let me just see another thing right here. I'm going to go to potential ball-ball collisions, and I'm actually going to try outing the number of collisions that we found, the number of potential collisions, so that we can see just how many collisions we reduced everything to. So I'll out that right here, and just recompile the program and run it, and I'll just add some balls. So I've added 400 balls right here, and this is the number of collisions it's checking, the number of pairs of balls it's checking for collisions. And this number is sort of fluctuating between, say, 500 and 800. So we've reduced things quite a bit. We've reduced the number of pairs of balls that we have to check from, say, 500,000 or 50,000 or so to about 600. So we actually have narrowed our search down quite a bit using octrees. And octrees are this one method that we can use for collision detection. It's useful for this particular kind of problem, but as I mentioned, there are other ways to do collision detection. This is just one particular example, and hopefully it'll give you an idea of how you can use collision detection in different kinds of programs, different techniques that you might use.